Welcome everybody to today's JAC. It's a great pleasure to have Rachel Sommerville visiting as part of the visitor program of OAS. Rachel, well, is a very renowned expert on galaxy formation models. She did a PhD in the cruise, then did postdocs in the Hebrew University in Jerusalem and in Cambridge. Then a professor at Michigan University, then staff position at MPAA in Heidelberg, then back to the US at Space Telescope, then Rutgers, and finally now she's at the Flatiron Institute in New York. Rachel is, as I said, is a leading expert on galaxy formation model. You probably know her for the very famous and very inspirational review with Romil Lave. Yeah, we are eager to learn what you're doing on the last few years.
Thank you so much, Roberto. So thank you to Roberto for inviting me and to the director for supporting this visit. I've had a wonderful week so far in your beautiful city, and I've also been incredibly impressed by all the science that's going on here. I've particularly enjoyed meeting some of your young colleagues and discussing science with them. So thank you very much for having me. Oh yeah, can we make that?
Yeah, I think you have to do it.
Do I have to do it again? Okay, give me one moment here.
We don't see anything.
Oh, you don't see anything? That's not good. Do you see the slides?
Not really.
Not really. You should, we see it here on another computer.
Excuse me.
I
other
see
people on-
the slide. I see the first slide.
You see the first slide? Well, you'll see the rest soon.
Scusi, venga qua, cosa ha detto?
Si deve mutare.
Oh, I don't know. Can you go on with your slide to see if it... Oh yeah,
Yes,
it works.
we
It
see
works all
that
right.
now. Thank you very much.
Okay,
We see that.
you
Thank
see that.
Okay.
Wonderful. No problem. Okay, so I think one of the universal questions that we ask as human beings is, how did we get here? And we know a lot about the universe at a redshift of 1100 from the cosmic microwave background radiation. We know that about 1 billion years after the Big Bang, stars were able to produce enough ionizing photons to ionize most of the hydrogen in the intergalactic medium. But in between, up until now, we haven't known very much about the first stars and the first galaxies. So we think that the first stars ended the cosmic dark ages at around a redshift of 20, maybe a couple 100 million years after the Big Bang. And then the first galaxies started to form. But we really didn't know exactly when the first galaxies started to form, what their properties are, what their stellar populations are like, how different they are from local galaxies, how different is their interstellar medium. And in particular, as theorists, we'd really like to use these objects as a sort of a laboratory to test our theories and our understanding of galaxy formation. So what's going on in this very early universe that might lead to the onset of star formation and galaxy formation? So of course, we believe that the scaffolding of galaxy formation is dark matter, collapsed structures of dark matter that we call dark matter halos. And as the universe evolves, the overall density goes down. We know that dark matter coalesces and collapses to form larger and larger structures. So if we made a diagram of the dark matter halo mass function, just the number of these collapsed objects as a function of their mass, we would see from redshift 15 in the blue to redshift of 8 in the red here, quite rapid evolution of the number of massive halos over this relatively brief time period, right? Only a few hundred millions of years. So structures forming very rapidly at this time. And this is important because we know that below a temperature of about 10 to the 4 Kelvin, that gas cools very inefficiently, right? So there's no heavy elements, there's no metals, just hydrogen and helium. And cooling by molecular hydrogen is rather inefficient. So this temperature of 10 to the 4 corresponds to a halo mass of a few times 10 to the 7 or 10 to the 8. So in these low mass halos that are very common at earlier epochs, galaxies basically can't form because the gas can't cool. Okay, so as we start to form these more massive halos, we should start to get gas cooling and the onset of star formation. And of course, then it gets complicated, right? So the moment stars start to form, then the massive stars affect their surroundings through what we call stellar feedback, which I'll be talking about quite a bit more. And perhaps we also start to form eventually the first massive black holes, which then also release lots of energy, drive winds, etc. So, you know, again, this is a one slide, super brief summary of a huge field, which of course has been summarized in some reviews that you can refer to for more details. But so one of the puzzles in galaxy formation is if we look in the nearby universe, we know that galaxies are very bad at making stars, right? So they're a bit like teenagers. They're inefficient and they can't hold on to anything, right? They can't hold on to their baryons. So particularly in relatively low mass halos, so this is showing the mass of the dark matter halo. This is now at the present day, redshift 0. Our Milky Way lives in a halo that's about 10 to the 12 solar masses. And there, halos are able to convert maybe a few tens of % of the available baryons into stars. Down at 10 to the 11 and below, galaxies are only able to convert a few % of their baryons into stars. So why is this? Well, I like to think about this as sort of having two origins. One sort of local. So in stellar nurseries, in giant molecular clouds, the moment massive stars start to form, they produce photoionizing radiation, which heats the surrounding gas. And there are also stellar winds from the photospheres of the stars themselves, which can disperse the clouds and halt any further star formation. And so in the local universe, when we look on molecular cloud scales, we see this inefficient star formation. So the clouds only convert about 1 or 2% of their gas into stars per free fall time. Okay, we know this from observations. And then when supernovae start to explode, the supernovae can drive large scale winds. Of course, we see again observational evidence for these galactic scale winds that then can evacuate much of the gas from the interstellar medium and make the overall baryon fractions low, as I just showed you. Okay, so in order to understand galaxy formation, we'd like to make detailed models and simulations of all of these processes that I've been sketching out for you. And there's been huge progress in the last decades in creating these detailed numerical hydrodynamic simulations, where we solve the equations of gravity, thermodynamics, hydrodynamics, possibly magnetohydrodynamics, right, for particles or grid cells, depending on the codes. And we get these wonderful, very detailed animations and maps of gas density, gas temperature, stellar density, galaxy properties, etc. So these are wonderful, wonderful tools for studying galaxy formation in great detail. And there are now a large number of groups that have independently created these simulations, including particularly focusing on the first billion years of cosmic evolution. However, there are some challenges associated with simulating these processes, as you probably all know. And one of those is dynamic range, right? So the processes I've been describing of stellar feedback, black hole formation, black hole feedback are occurring on scales of probably less than a parsec, right? Parsecs to subparsec scales. Whereas these large volume simulations typically have mass resolutions of more like 10 to the 4 to 10 to the 6 solar masses, very far from the mass of an individual star, and spatial resolutions of a few hundred parsecs to a kiloparsec. So obviously we cannot, resolve supernova explosions or, winds from massive stars. So all of these simulations have to adopt what are called subgrid recipes to represent the physics occurring on the scales below what can be explicitly resolved. And those recipes are inherently very uncertain. Each group sort of does it in a slightly different way. So we have to keep that in mind. Another limitation, of course, is dynamic range. So what I've tried to sketch for you here is this sort of trade-off between resolution. So this is the mass of a dark matter particle, where this is going to smaller masses. So this is sort of better resolution going to the right, finer particles, and this is volume. And this line is showing you the volume of a typical JWST field at the redshifts that I will be focusing on. So around a redshift of 11, it's about almost 1 million cubic megaparsecs. Of course, we now have multiple fields of this size. And this is showing the atomic cooling limit that I mentioned before. And then if you wanted to resolve the formation of the first stars, pod3 stars, you'd have to go even higher in resolution. So you'd like to be over here, right? And instead, most simulations are, either very small in volume and high resolution, or much coarser in resolution if they're achieving these larger volumes. So another way to go is to use a technique called semi-analytic modeling, where we use merger trees from a dissipationless n-body simulation, a dark matter only simulation, which tells us how the dark matters grew in mass and merged together with other dark matter halos. And then within this framework, instead of solving PDEs, we solve ODEs. So we assume that everything is spherical, and we just track how gas flows in to the galaxy, forms stars, stellar feedback, blows winds out, etc. So you have basically a set of coupled ordinary differential equations representing the same kinds of physical processes, star formation, stellar feedback, black hole growth, etc. And in the most recent generation of semi-analytic models, we can actually motivate these recipes based on numerical simulations, right? So we can kind of make sure that our story is consistent between the more detailed but expensive simulations and these computationally efficient but more approximate techniques. And so the advantage is that because these are so much more computationally efficient, we can achieve a higher dynamic range, right? So we can span larger volumes and still get down to the resolution of these first galaxies that we're interested in. Okay, so already, even before James Webb launched, we knew a fair amount about early galaxies back to a certain point from studies with Hubble, Spitzer, etc. So many of you are probably familiar with these surveys done with Hubble and followed up with many other instruments. So all of these surveys, and this technique now goes back to the 90s, use a technique for finding high redshift galaxies. So of course, if you look in an image like this, a lot of the galaxies are relatively nearby, right? So you want to pick out the distant galaxies if you're interested in the early universe. And you can do that using this line and break technique, right? So of course, the SED cuts off at 912 angstroms, and as galaxies redshift, that break shifts to longer and longer wavelengths. So you're looking for galaxies that you see at longer wavelengths and then that drop out at shorter wavelengths. However, of course, Hubble only went into the near infrared. So we reached sort of a cliff at a redshift of 9 or 10, where things just shifted all the way out of where Hubble could see. So there was a fundamental limit on the largest distances that we could study galaxies, the most distant galaxies that we could identify. Now, we had large samples of galaxy candidates, even going out to redshift 10 and 11. They were typically identified just with Spitzer Space Telescope. And this was already sketching out an interesting picture. So this is a famous diagram, the Dow diagram, showing the cosmic star formation rate density. So the total rate of star formation of all galaxies in the universe divided by their co-moving volume. And we know that this rises to about a redshift of 2, sometimes called cosmic noon, and then drops again to the present day. So with these pre-JWST surveys, we were already, as I mentioned, able to probe out to a redshift of 10, but different studies were showing different kinds of evolution. So some studies showed sort of a flatter decline out to higher redshifts, some showed a break and a steep decline out to higher redshifts. And of course, what we all really wanted to know was, what happened at even earlier times, even higher redshifts. So from the theory point of view, we have our numerical cosmological simulations, we have our semi-analytic models. And as I mentioned, all of these models have these uncertain subgrid recipes. So what do? We sort of massage and tune those subgrid recipes to match the properties of galaxies in the nearby universe, where we know a lot about galaxies. Okay, so in particular, in order to match nearby galaxies, we have to assume this low star formation efficiency, right? This few percent per free fall time star formation efficiency, and rather strong stellar feedback in order to achieve those low baryon inflections that I showed you. So now we can do the experiment of saying, okay, what if we leave all those subgrid recipes alone? They're tuned to the local universe. And now let's just see what our models predict at earlier times. Okay. So this is the exercise we did here in a series of papers before JWST launched, led by my former student, Aaron Jung. And this is showing luminosity functions, so the number of galaxies as a function of their rest frame UV magnitude. Here going back to redshift 10, which was as far back as we then dared to go. In retrospect, we should have dared to go even further. And to our surprise, when we did this, we actually found really excellent agreement between our model predictions, which remember were tuned at redshift 0, all the way out to redshift 10. And there was also very good agreement between different methods, different simulations. So in these papers, I don't have time to show you today, but you can go look at these papers if you're interested. The numerical simulations, the semi-analytic models all agreed fairly well out to a redshift of 10. So it looked like a nice picture where, okay, maybe we actually understand what's going on. So now, of course, as you all know, in 2021, we all got, I think, the best Christmas present that the astronomical community, perhaps humanity, has ever gotten, since the first one, maybe. And JWST had an absolutely flawless launch. The commissioning went beautifully, everything went beautifully. And on July 13th, 2022, the first images were released to the public as well as to the science teams. And I think you all probably have been hearing a lot about the results since then. And I think, again, you all know what JWST's two superpowers are. So first, the largest aperture mirror that's ever been flown into space, much larger than Spitzer or Hubble, and the infrared, the far infrared sensitivity, right? So the sensitivity for near CAM going out to 5 microns, and for MIRI going out to 25-ish microns. So of course, this is wonderful for studying dust, planets, etc. But it's also wonderful for studying the early universe, where, of course, the UV and optical light from stars has been redshifted into the infrared. So now, where I showed you we were sort of falling off a cliff before, we can actually go all the way out to redshift 20 in principle. If the galaxy were bright enough, we would see it with James Webb, right? We have the wavelength coverage with NearCam. We have these 8 NearCam filters. We can do this dropout trick all the way out to very high redshift. So I was very fortunate to be a member of one of the early release science teams, which planned some of the first observations that were taken with Webb. So these observations were taken in June and December of 2022. And this program was called SEERS, Cosmic Evolution Early Release Science Survey. And we used 6 of the instruments on JWST to study many aspects of galaxy formation. Again, I can't begin to tell you about all of the science that's come out of SEERS. But of course, one of our focuses and goals was to study very early galaxies. So I think it was a day or two after, I know it was on the weekend, I was actually traveling. We got an email from Steve Finkelstein, the PI of SEERS, saying, I found a redshift 14 galaxy. Like, immediately, we broke that record that had been set before of, redshift 10 or 11. And so we saw this classic signature, right? Dropout in the shorter bands, strong detection in the longer bands. Turns out this is actually redshift 12, not redshift 14, but okay, right? So we had to reduce our data better and so forth. So this galaxy is called Maisie's galaxy. It was one of the first, sort of record-breaking galaxies to be detected with JWST, and then the floodgates opened. Right. So then many teams started finding more and more of these very early galaxies. The other incredible thing about JWST is it has its own spectrograph on board, NIRSpec, which is also infrared sensitive. And NIRSpec spectra, I know many of you are working with NIRSpec, and so they are insane. They are superb spectra. So rather quickly, we and other teams started to do spectroscopic follow-up of these high redshift candidates. And in most cases, the photometric redshifts more or less held up, right? So if we thought the galaxy was redshift 12, it was redshift 12-ish. There were a few notable exceptions. So there were 2 candidates at redshift 16, which turned out to be redshift 4.9 because there was an emission line that just kind of went in a weird spot. But so mostly the redshifts have been fairly robust, and there are now fairly large samples of spectroscopically confirmed galaxies. So again, I can't even now fit all of the programs, extragalactic sort of high redshift focused programs on one slide. This is a fairly complete summary as of cycle 1, which of course, now we're going into cycle 4 soon. But we now have sort of this nice wedding cake. This is showing the area on the sky of these different surveys and the depth. So we have, some deep, smaller area programs like NG Deep and JADES, and then some wider area like SEERS, Primer, Cosmos Webb, etc. And then of course we have the lensed fields where we have galaxies that are magnified behind lensing clusters. Beautiful work being done with the lensing fields. So just an absolute cornucopia of amazing data that we could never do before. So very, very, very exciting. And so we can now construct luminosity functions, right? Count galaxies as a function of their rest frame magnitude out to redshift 14. At redshift 11, I'd say this is quite robustly measured. We have lots of spectroscopic redshifts. We have pretty good statistics. At redshift 14, you can see the number of galaxies that went into this, right? It's just a handful. We have a couple of spectroscopic confirmations out to redshift 14. I believe the record holder right now is like redshift 14.3, something like that, right? So this will continue to build up. And what this revealed was a bit of a surprise. So remember I showed you that before JWST, people were showing that the number of galaxies was maybe even declining more steeply as we went out beyond redshift 8 or 9 than in the past. What we're finding now, if we just plot the number density of bright galaxies, so these are galaxies brighter than a magnitude of 20, sort of where that knee is in the luminosity function that I showed you, what we expected was sort of the blue line. This was the optimistic expectation, if you like. And instead, we see this very flat evolution, very slow evolution, all the way back to redshift 14. The number density of bright galaxies has hardly changed back to redshift 14. And that is surprising because remember I showed you how rapidly the halo mass function is building up at this time, right? So if you look at sort of the massive halos, this is just showing the number density, cumulative number density of halos of different masses. So these are more massive halos going down to less massive halos. We think these galaxies probably live in sort of 10 to the 10 or 10 to the 11 solar mass halos. The number density declined by 2 orders of magnitude over that same period. And yet the number density of galaxies is almost staying the same. So perhaps not surprisingly, if we now looked at all the model predictions from before JWST launched, right, where we had baked in this sort of calibration to the local universe, they all predict a much steeper decline in the number of bright galaxies as you go out to higher redshift. And the different models also are very different in their predictions. And in particular, this discrepancy, so now this is kind of zooming in on redshift 11, where as I mentioned, we think that this measurement is quite robust. The models particularly fail at the bright end. So, you know, some of them can maybe get enough faint galaxies, but they really struggle to produce the abundance of bright galaxies observed by JWST. So I want to just zoom in on one of these theoretical predictions that by myself and my collaborators. So this is also work led by Aaron Jung. So we realized that in order to do this work at the very high redshifts that JWST was probing, we actually needed better n-body simulations because we wanted to span this very large dynamic range. So Aaron constructed a new suite of n-body simulations with different volumes and different resolutions. So we basically stack a small high resolution box with a bigger lower resolution box, and we stack up a whole bunch of boxes so that we can achieve this very high dynamic range. And we also save a lot of snapshots at these high redshifts. So previous simulations didn't save very many snapshots at early times because they didn't care, right? But we care a lot. So we now have saved very, very fine snapshots. And then we ran our models. Like, so again, these are the pre-launch models, the vanilla models, I like to call them, normalized to redshift 0. And here's just sort of zooming in on our predictions from redshift 9 to 14. So as we saw before, out to redshift 10, everything looks good. I don't know if I said this is a luminosity function again, UV luminosity function. And here the models do not include any dust. Okay, so really there probably is dust. I'll come to that later. But by redshift 11, the models start to look a little bit low compared to the data. And by redshift 14, they're certainly quite low. Okay, I think I'm actually going to skip the next 2 slides, but if you want to know about massive galaxies and breaking lambda CDM and all of that, ask me later. TLDR, lambda CDM is not broken. Okay, so this was all in terms of luminosity, right? So we can make predictions from our models in terms of UV luminosity, which is what we observe. We can also try to estimate the stellar masses of these galaxies from their spectral energy distributions. Now, this is, of course, this has its own can of worms set of caveats and assumptions, but we can try to do this. So this is a plot from a recent paper by Harvey et al. The red is showing their estimates of the stellar mass function going out to redshift 12-ish. And ignore this black line and this cyan line, which are kind of post, these are people trying to now fit the JWST results. These are the sort of pre-launch models, again, which also, in addition to underproducing bright galaxies, appear to underproduce massive galaxies. Okay, so sort of good to look at both that in both ways. So what's the answer? How do we solve this problem? There's, of course, been a flurry of papers, this is not even all the papers, proposing different solutions to this problem. I've tried to sort of summarize them here. I think there are 2 basic ways to solve the problem, right? One, you make galaxies brighter. Maybe the stellar initial mass function has more massive stars. So for a given amount of stars, you get more UV light. Maybe there's some AGN contributing to the UV light. It's also been shown that if star formation is very bursty, then some of those low mass halos, which remember how much more abundant the low mass halos are, they can pop up and populate the bright end for a short amount of time. And that maybe can solve the problem. I'm slightly dubious whether that can solve the problem out to redshift 14, but we'll see. And probably you want to not have a lot of dust, right? And again, I'll come back to dust later. So that's one class of solutions. The other class of solutions is to make more stars, right? Make stars more efficiently. And this is the picture that I've been working on that I want to tell you about for a bit now. So one of the things we know from the observations of these early galaxies is that they are very small. Their sizes are maybe 100 to a couple hundreds of parsecs, or even smaller. So this is showing observations from Morishita et al. Showing the star formation rate density, surface density, as a function of stellar mass. So nearby galaxies, where this means like up to redshift 3-ish, 4-ish, live down here. And the high redshift galaxies, redshift 5 to 14, you can see that their surface densities are orders of magnitude higher. So presumably their gas surface densities are also orders of magnitude higher than lower redshift galaxies. So I made a super simple model here where I just assumed that the size of the gas disk in the galaxy tracks the virial radius of dark matter halo. Okay, and we know that, of course, dark matter halos are denser. They have a smaller virial radius for their mass in the past, just because the whole universe was denser, right? So they sort of track the density of the universe at the time that they collapsed. And oddly enough, if you sort of stick some observational points on here, going back to these early times, it tracks pretty well. Okay, so you can kind of say, well, yeah, the universe was denser, we're going to make denser galaxies. Sounds too simple to be right, but this seems to be what the data are suggesting. So what are the consequences of these high densities? There's been work on this for several years now. So again, this is a situation where I feel like theorists should have predicted this before the universe told us, but okay. So what I want to show you now is a simulation by one of the postdocs at CCA, Sham Menon, where he simulates sort of an individual molecular cloud, or a protocluster, if you like. So it's like a 10 to the 5 solar mass cloud of gas. But he does full radiative transfer, and he includes all of the stellar evolution and stellar feedback, etc. Okay, so what you're going to see is on the top left, a cloud with a surface density of 100 solar masses per square parsec. This is sort of typical of a dense-ish molecular cloud in the local universe, right? And then this is 10 to the 3, 10 to the 4. This is probably typical of these high redshift galaxies, and 10 to the 5. Okay, so let's play the movie. And what you'll see is, as I was describing before, this cloud is very quickly dispersed by the mainly by the photoionizing radiation in this case. Whereas the denser clouds keep forming stars for many, many freefall times. So this guy gets dispersed in like a freefall time or a couple freefall times. These guys keep forming stars for many freefall times. And while this guy only turns about 10% of the initial gas into stars before it gets dispersed, these dense clouds can convert 90% of their gas into stars before they get shut off by their own stars. So what I've done now is to imagine, okay, let's suppose these high redshift galaxies are forming stars in these clusters, these sort of proto clusters, if you like, or clumps, clouds, whatever you want to call them. As an aside, we actually see evidence for this very clumpy star formation from lensed objects. This is one of the famous ones called the cosmic grapes, where you can see that the galaxy seems to be made up of these many, many clumps. This guy's at redshift 6-ish, I think, but there's some at higher redshift. And I built this incredibly simple analytic model, which again is based on ideas that have been around for a long time, that just says, once you've deposited enough momentum to unbind the gas for a given gravitational potential, then you stop the star formation. Okay. And it turns out, so this is the star formation efficiency, the fraction of the gas that gets turned into stars before the cloud is dispersed as a function of the cloud surface density. So again, this is sort of local universe densities. These are, maybe these high redshift densities. The points here are from Shams simulations that I just showed you. And the black line is my super simple dumb analytic model based on this very simple idea. And then I also need a time scale. So I need to know, how long does each cloud keep making stars? So again, I just take that from the simulations. And then voila, I have a star formation rate for my cloud, which depends on the density of the ISM from which the clouds are forming, right? And again, I'm making a simple assumption that denser ISM leads to denser clouds, so that they just scale by some simple factor. So now we can plug this in to our cosmological framework, right? So now instead of using 1% per free fall time for this cloud scale star formation efficiency, we scale it with the overall density of the gas. So that what that means, of course, is that the efficiency is going to be higher in the early universe when the galaxies were denser. So now here's our UV luminosity functions again, going from redshift 9 out to redshift 17. And the one thing we don't know is what fraction of the gas is in these clusters or clouds. Okay, so we've just treated that as a free parameter, and we can have an upper limit, which is all of the gas is in clusters. That's this top line. Then you actually overpredict the observed number of galaxies, even maybe out to redshift 14. And if you assume between 10% and 50%, which incidentally is consistent. So for example, that cosmic grapes, about half of the star formation they estimate is happening in those clumps. So 10% to 50%, I think, is not crazy. Then you get sort of the lines that more or less seem to live very close to the observations. In addition, now we can look at the stellar mass function. So as I mentioned, we're not just making galaxies brighter, we're making more stars, right? We're making stars more efficiently. So, this green line is similar to a dense gas fraction, a cluster fraction of around a half. And that seems to match the observations pretty well up to high redshift. Again, these are very uncertain. Okay. So that seems intriguing. Really quickly, what about dust? Everything I've shown you assumes that there is no dust in the universe. However, if we make sort of vanilla assumptions about dust yields from supernovae, dust destruction rates, etc., there should actually be quite a lot of dust already by redshift 11 in these galaxies. And yet, if we look at the UV slopes, right? So how red is the UV spectrum, the spectra of these galaxies? We can fit the UV slope. By redshift 11, there's almost no room for any extinction. Okay, there's almost no room for any reddening by dust. So this is one of the puzzles of the JWST observations. And one suggestion, of course, there's many ways to solve this problem. One suggestion made by Andrea Ferrara and collaborators is that if the star formation rate density is high enough, you might push the dust out of the galaxy. So Andrea proposed a critical specific star formation rate above which you would eject the dust. Okay, so I implemented that in my model and found indeed at redshift 11, there's almost no reddening and no attenuation by dust. So we still match the observations pretty well. But so the dust model is shown by the dashed line now. By redshift 8, there is a significant amount of dust. Again, we know this, right? We see dust with ALMA. So the dust is ramping up because the average specific star formation rate of galaxies is dropping, just as Andrea predicted. Okay, I want to wrap up very soon, but I just want to make one aside, which is that Another intriguing result from JWST is with these gorgeous near spec spectra, we can measure lots and lots of emission lines, and we can constrain chemical abundances, right, of elements in the ISM. And if we look at these so-called nitrogen emitters, so objects with strong nitrogen lines, we can constrain nitrogen to oxygen versus oxygen. And we see a characteristic pattern for these abundance ratios in the local universe. And the high redshift galaxies, so these are redshift 6 to 8, which is sort of the highest redshift we've been able to do this work so far with JWST. They show very different abundance patterns, elevated nitrogen ratios. Curiously, similar to stars and globular clusters in our own galaxies. So to me, this is maybe support for this picture where high redshift galaxies are forming a lot of their stars in these dense clusters very efficiently, and that would also lead to these abundance patterns. Also, an aside, from line ratios of different ionization states of the same element, we can estimate electron densities, and they are also very high. So that's, again, consistent with the ISM being very, very dense. Okay, so in the last 5 minutes or so, I basically want to tease you by giving you some dessert and maybe a choose your own adventure. Okay, I want to leave some time at the end for you to ask whatever questions you want to ask. But so I guess, you know, the fourth surprise from JWST in the early universe was the discovery of supermassive black holes all over the place, as it's been stated. So one weird thing that was discovered are these so-called little red dots. So these are objects that are unresolved in NIRCam. You know, they basically are point sources. And if you look at their SED, they are very blue in the UV, and they have this weird V-shaped SED. So they're red in the optical, blue in the UV. And there's a huge amount of debate about what these are stars, or this a reddened AGN combined with stars. So there's many ways to make this SED, but many of these objects also have broad lines, right? Broad H alpha, indicating or strongly suggesting that they are powered by a black hole. So we're now able to make AGN luminosity functions going down to much lower luminosities. So this is sort of redshift 5-ish, redshift 7-ish. And of course, we knew about the bright quasars, right? Like the ones that Roberto and others study from the wide surveys like Sloan. So these objects are much fainter in the UV, and also much more abundant than those very bright quasars. And as I mentioned, from the broad lines, if you're brave, you can use the local scaling relations to get black hole masses. So this, you know, again, there are many papers that have done this over the last year or so. This is a recent one by the Sears collaboration, led by a student at UT Austin, presenting a black hole mass function. So the number of black holes as a function of their mass at redshift 5-ish, going down to 1 million solar masses. And again, so the sort of familiar black holes are up here on 10 to the 9 solar masses. So now we're going several orders of magnitude down the black hole mass function, and these things are quite abundant. The other weird thing is, if you think you can measure stellar masses, so some of the objects you can actually resolve the galaxy, right? You can see the stars around the galaxy, you can try to estimate a stellar mass, or you can get a dynamical mass, right? For the stars. And there's a well-known relationship between stellar mass and the black hole mass in nearby galaxies, which is about 1 to 1,000, right? These galaxies live up here. So their black holes seem to be very massive compared to their stars. Again, if you trust all of these measurements and scaling relations. So one of the big questions, of course, is how did these black holes form? And the three main mechanisms for forming what we call seed black holes are you have a massive star, then they should be very common, but pretty light, 100 solar masses or so. Or you collapse the center of a star cluster through what's called runaway collapse in the very center of the cluster, and then you might get 1,000 solar mass seeds. And those might be common, they might not be common, we don't know. There's been famous work on the so-called direct collapse mechanism, where you basically get a cloud of gas to just collapse directly to a black hole. And then you could get very massive seeds, what are called heavy seeds, but those should be very rare or they may not exist at all, right? So there's been a lot of speculation that these observations of the overmassive black holes strongly support this heavy seeding picture. So what do we know so far about this question? And do these observations really constrain seeding yet? I would argue no, again, to cut to the chase. So this is the black hole mass function, again, from Anthony Taylor's work. And so interestingly, we took a bunch of models, so flares, Santa Cruz SAM, CAT from the Rome group, which were published before these observations, long before these observations were taken, right? So most of these models have been around for a while. They actually lie right on top of the observations. And, so maybe you don't need to do anything that special to get these black holes. And then we also made a toy model where we just tried putting in different kinds of seeds and growing them at different rates. And we found that at least by redshift 5, you can't really say that much about the seeding from the observed black hole mass function, right? It's very degenerate with how rapidly the black holes accrete. But the real problem, right, is, okay, I just showed you simulations that reproduce the black hole mass function, but should you be impressed by that? No, absolutely not, right? I do not trust them at all. And the reason I don't trust them, well, there are many reasons. But one reason, right, is, remember I showed you the simulation mass resolution is 10 to the 5, 10 to the 6 per particle. And all of these seeding mechanisms are, of course, happening on much smaller scales. There's a litany of other reasons I don't trust the simulations, which let's not go into. So what I'm working on with Aklan Bomik, Laura Blecka, and others is a new suite of simulations. So these are now numerical simulations, zoom-ins or small boxes, where we try out many different seeding models, try to sort of explore the parameter space of different seeding models, and then we're developing analytic subgrid models and also machine learning based subgrid models that now we can implement into our larger volume cosmological simulations or our semi-analytic models. And I'm going to skip over the results. You can ask me if you want, and give you my last teaser before I conclude, which some of you may be interested in. So this is somewhat disconnected from what I've just been talking about, but I couldn't resist since I know there are quite a few people here working on AGN winds and quenching and so forth. So one of the big uncertainties, of course, in all this modeling is how the black hole feedback works. So we've been developing a new implementation of AGN-driven winds associated with radiatively efficient accretion. And this model is called Mistral, being implemented by these people. And again, basically, if you want to know more about this, please ask me. And I will leave you with my summary and take your questions. Thank you very much.
Questions, Chris? I have one.
Should we put the lights up a little bit? Should we put the lights up a little bit? People wake up. Yeah, just a few bit.
Okay.
Yeah.
So
Ex-
about one of the scenario you're working on, which is this higher star formation rate
Yeah.
caused by a higher surface brightness of primordial galaxies. So this higher formation rate, with respect to what was expected, it should not impact cosmic realization evolution. I mean, given that cosmic realization should mostly due to ultraviolet photons produced by these stars. So
Yes.
So in which way is this impact relevant, and in which way compared to the evolution of the colorization we infer from CMB or
Great question, and this is something we're working on, which I just didn't have time to talk about. So a lot hinges on the escape fraction of the ionizing photons. In these very dense clouds, for most of their lifetime, the ionizing photons can't escape very efficiently, right, as you would expect. So I think you're right that it probably will not have a big impact on reionization. But it turns out, and so Sham actually shows this in his paper, that you can sometimes have channels that are cleared where the ionizing photons can leak out. So he actually predicts escape fractions as a function of surface density, which then we can fold in to make more quantitative predictions of that. They're actually now, so there in the past was kind of, people were worried about not producing enough ionizing photons or not getting enough out. Now I think we may actually have too many, right? There are people claiming that like we're overdoing it with reionization.
Any questions? Okay.
Thanks for the talk. So, my question is related to the results on sheet
14.
Yeah. So, do you think that causal variance is playing some role in the discrepancies between observations and model?
Oh, very good question. That's an excellent question. Yeah, let me try to go back. So these fields are still very small, right? And in particular, the deepest fields are very small, right? They're 1 meter count pointing, so they're what, like 10 megaparsecs or less, something like that across. So this lower point is from the Sears field, and these higher points are from the James origin field, which is teeny tiny, but it's very fascinating. You may know this already. The two spectroscopically confirmed sort of record holders at redshift 14.3, there's 2 galaxies within 5 moving megaparsecs of each other, and maybe a third. So it's like, maybe it's a proto cluster over density, but yes, I think cosmic variance is likely very important because these objects are extremely biased. So if you happen to get an overdense field, then yeah, it's going to be high.
Siamo di là in
Over here? Yeah.
Very useful. I was wondering how your model that predicts very high efficiency conversion gas is combined with the dust ejection. Are those things happening at the same time? The dust ejection at the very end? If you eject all the dust, can you retain the gas?
Yeah, great question, and also one that we're looking at with Sham. I might even have a reserve slide here on that. I may not be able to find it easily. No. Yes. So from the same simulations, we're doing full radiative transfer, so we can track the escape fraction of the ultraviolet. I don't know if you can see this well, but so again, these are these different density clouds, and this is showing how the dust is basically getting cleared. So there's a characteristic time scale which also depends on the cloud density. So we now want to fold this in to our modeling. I mean, it's the same idea as the Ferrara model, right? But we can fold in timescales in more detail now.
Yeah, so another question about this high efficiency. So you showed how you can this high density, the high redshift,
Yeah,
could lead to very high efficiency, close to 100%. But if I understand correctly,
on the cloud scale.
yeah, exactly.
Yeah.
So there are observation claims
Yeah.
that the variance, the fractional variance in the whole halo that turn into stars is close to 100%. So, but your model does not explain that. Am I correct? Or like, how do you then conclude that lambda CDM is not broken? I
Right.
guess there are other reasons.
Well, so I mean, the stellar masses are still, the revised stellar masses are not close to all of the baryons in the halo. The very early results from Lebesgue and so forth did suggest that, but those have all come way down. And the objects that were breaking the universe, a lot of those were actually little red dots, right? So they were probably actually AGN, and the stellar masses were nonsense.
I guess. I'm
So
thinking more
according to these most current estimates of the stellar masses, you're not that close to all of the baryons having to turn into stars.
I was thinking more of like the Glazebrook kind of things where.
Right.
Galaxies reproduce
Yeah.
the whole
Yeah.
history and they
Yeah.
still claim that
Right.
the efficiency of the hail is 100%.
Yeah. So then you have to believe that they can reconstruct the history that well, right? So of course, the picture that I'm proposing will lead to more early star formation. So maybe it's in better agreement with those kinds of observations. I think it would be very interesting to try to compare, right? Like do the same analysis on our star formation histories and see if they're consistent. But yeah, we're still not converting all of the baryons into stars, even at redshift 14. But that would actually violate the observed UV luminosity functions, right? Unless you somehow have very weird stars.
Julia?
Hi, I was curious about your new small cosmological boxes, and I was wondering what's the redshift range that you're running them for? Because I mean, you're trying to reproduce this, which is great.
Yes.
But so also again, the large boxes, they don't reproduce the
Right.
number, but they're not also designed for it.
Yeah.
So
So
I
these.
was wondering, sorry, if what's your point? What's the future? If we will have to do subgrid physics that really heavily depends on redshift and changes with some parameterization as much time.
I think that's what we have to do. Yeah, so exactly. These high resolution boxes are only run down to like redshift 5. We have some larger boxes, 20 megaparsecs on a side, that we run to redshift 0, but with a lot of caveats because also the large modes are not captured then. So but what we really think we have to do is to study how the physics is working in those higher resolution simulations and then put that with a subgrid into our larger volume simulations. I think that's the only way we can do it.
So you see when you run it to redshift 0, you see bigger things.
We haven't done it yet.
Okay.
We're still trying to understand the subgrid physics in the high resolution boxes.
In the slide with the luminosity function and
Yeah.
the function of redshift, you have also prediction of redshift 15, 17.
Yep.
I guess you have also higher redshift where no galaxy seen so far. Is that because the fields are too small, or you expect some galaxies those redshifts already be present in the existing data?
So this is limited by, sorry.
They're also missing at 13.
Yeah.
There's just no observational
It's very interesting.
points because people are averaging over a redshift bin and there's just no bin at 13. Like they're averaging from 9.7 to 13. And then this is like 12 to, it's just it's the observer's fault. It's not our fault. We have galaxies at redshift 13. But to your question, why are our lines cutting off here?
No, but if on the basis of those models,
Yes.
you expect that some galaxies, those redshifts are already present in the data, but are not seen yet.
Exactly. And of course, we can test this, and I hope we will test this with future AWST observations where we will try to go even deeper. Right. So of course, even though these are the same absolute magnitude, they're much fainter in apparent magnitude. So you have to go even deeper to see them. But the reason the lines are cutting off here is just the volume of our n-body box. So we're actually now running an even bigger, we're running like the next one up for our n-body simulations because these galaxies are very rare. Those massive halos are super rare. Yeah.
Okay.
Well,
Very quick.
Maybe I can have a naive question.
Sure.
If we have a top-heavy initial mass function.
Yes.
How can we overcome the strong feedback from mass star and get a high star formation efficiency?
That is a great question. And we actually looked at that in a paper by Sham Menon. So you can look at the paper. You might think that if you had a top-heavy IMF that you would again, reduce the efficiency of the star formation. It turns out that in these very dense clouds, even with a top-heavy IMF, you still get very high efficiencies. Yeah, so you can have a look at that paper. It's from 2023 or 2024.
Okay. Well,
Can we receive the transparency, copy of the transparency? Or you can put the copy of the transparency of this very important.
Yeah. I'll be happy to do that. I'll be happy to share the slides.
And okay, we send you an email and how can we receive?
And also Lorenzo Napolitano has a question. Lorenzo, if you wanted to speak.
Yeah, can you hear me?
Yes. Yeah. Hi, Lorenzo.
Hi, thank you for the review. I just wanted to ask you if from the simulation point of view, in the very next future, can we actually investigate more about the enriched metal poor nature of those observed very high redshift galaxies at redshift, let's say, higher than 10?
Yes, absolutely. I mean, so these detailed numerical simulations, and in fact, even the semi-analytic models are coupled with chemical evolution models, right? So of course, this depends on the yield tables, which are uncertain, on how metals are dispersed within the ISM and you know, metal loading of winds and so forth. So there are many uncertainties, but I think the exciting thing is that we will have beautiful observations to constrain, and that will actually constrain things like the feedback processes and the yields. Of course, there's also gorgeous data on nearby galaxies, on resolved stars, right, on metal abundances and chemical abundance ratios of resolved stars, which is actually also a very powerful constraint on these processes. But I didn't show you any of this, but you know, all of those quantities are being predicted by these models.
Okay, thank you.
Sure.
okay. Well, thanks.
Well, that's exactly what we're trying to do now, right? Is to model the seeding self-consistently. So, well, my favorite idea is that these clusters that have the efficient star formation, they also produce a seed black hole center, right? Solid black hole. And maybe there are many clusters in a seed galaxy, and maybe those merge to form black hole. So maybe, but that's what we're now starting to work out, is like whether that all.
No models at the moment that are able to link this.
Right, because of this issue of dynamic range that I just mentioned.
Yeah.
Wonderful. Yeah.
Yeah. So I was just asking you, what about? Yeah.